Welcome back, and it's probably going to be a short lecture. However, it's a topic that's very dear to my heart, simply because in the history of robust stability and control, you know, original ideas started almost as old as early 1900s, when people were talking about classical control and things like that. But much of the work, the real work probably started in 1960s and things like that. And major results came in 1980s, and when I was doing my doctoral thesis in the 90s, basically it was still there, and then I caught the tail end of it, contributed a few key results to robust stability. But far more important is basically a lot of connections we have done is actually connect some of the classic results to basically many of the other classic results in literature related to nonlinear systems and things like that. And then in that sense, what you'll find in this set of lectures is a unique presentation of robust stability from the point of view of Lyapunov function theory and its extensions, right? So if one understands these connections, actually it's a eye-opener in many ways, because still most people in most textbooks treat these topics as completely separate, and then typically as soon as people start thinking about robust stability, they think of frequency domain and they remain there. But in reality, it is very much a theory that is actually quite connected to Lyapunov functions, for example, right? So we will start with reminding ourselves in terms of stability margins in the frequency domain, and then we will talk about extensions of that, and then the basic ideas of robust stability, and then specifically something called structured uncertainty. And why do we talk about uncertainties? Well, modeling uncertainties are inevitable in most applications. What does that mean? If you have a physical system and then we have a model for it, 90% or 100% of models are inaccurate, right? So there is always some difference between the actual system and what you have modeled, right? And sometimes the uncertainties are because you are unable to exactly measure the model, right? The other times is basically we want to ignore some dynamics because it's too complicated to model, and perhaps we have other methods of dealing with that kind of ignoring such models, right? So any model, we will definitely have these uncertainties. The only hope is these uncertainties are not going to be destroying the stability of the overall system. So therefore, people came up with these notions of margins. So you have, let's say, system stability. Now, do I have margin? I mean, am I actually on the boundary of instability, or I'm well within stability margins, where basically I have some region around which I can play around in terms of, even if I make a mistake in terms of my assumptions on some of the parameters and things like that, can I live with that uncertainty, right? So we'll remind ourselves Nyquist criterion, not exactly in every minute detail, but perhaps at a very high level. So the classical control approach of using Nyquist criterion is obviously, most of you probably know if you went through an undergraduate course, can be extended to multi-input, multi-output systems, which is of interest to us here, and eventually present this very sensational quantity or concept called structured singular value. And perhaps I will just showcase a paper that resulted in this particular concept, the original paper and things like that, right? But then what our goal is actually not really get into too many details of some of these methods. These are all frequency domain methods, and then they have a purpose, and it's nice and intuitive and things like that, and it has its methods, and then there's an entire toolbox dedicated in MATLAB that's based on structured singular value. We'll talk a little bit about the history, but our approach is actually sticking to state space methods, right? Because state space methods allow you to deal with nonlinearities and things like that. So therefore, it's a major task for us to connect these two worlds and then say that we are not going to lose anything by actually looking just at state space methods. Okay, I mean that's the objective. I mean it's not like we are sacrificing anything that was already well established or something like that. In fact, we will have only advantages when we actually move to state space methods, right? So let's actually remind ourselves a few things here. The Nyquist theorem, depends on this nice plot called Nyquist plot, right? I'm not getting into details and assuming that you have seen the Nyquist plot. What is this plot? It is a plot on the complex plane. Okay. So let's say we have some kind of transfer function. Okay. If you recall, basically that's the function that relates your input and output. If somebody is insisting on the definition, basically this is nothing but some output transfer function. Output Laplace transform is going to be dependent on some transfer function multiplying the input Laplace transform. And we have some nice interesting results that basically if G of S has poles in the open left half plane, then we have stability, bounded input, bounded output stability and things like that. These are the classical results, right? And there is a corresponding Nyquist plot, something that says basically, typically what we do is basically if we have some system like this, we will actually put a feedback, let me say some feedback transfer function controller. This is typically in our control, and let's say we assume negative feedback for some reference and some reference, and then basically you have this control input here, and basically by looking at what they call as open loop poles of this particular thing, and then number of encirclements of the point -1 and things like that, they conclude the stability of the closed loop system, right? And using that particular theory, basically then there is an entire concept of stability margins is developed. Let's say -1 is here, and let's say your Nyquist plot is here. So in this particular case, the Nyquist plot is not encircling the -1. If it is, it's fine, but let's say we'll consider the case of that encirclement also. So what margins talk about is, suppose if I imagine basically I'm multiplying this particular plot, how much should I multiply before it touches -1, and that that factor that multiplied when it goes to -1 kind of gives you the margin, right? So this multiplication factor enters your transfer function that corresponds to some kind of parameter becoming uncertain, things like that. So those are the stability margins, and typically the function that we draw, the Nyquist plot corresponds to G of S, K of S. So this margins we talk about, how much leeway we have in terms of the control, if we make a mistake in terms of putting the control. But it also can be interpreted as basically some multiplicative factor that we ignored in G of S, right? So stability margins were typically meant for understanding, the control uncertainties, but it actually has uncertainties of all kinds, right? So where is this -1 coming from? Basically, if I actually look at, I'm going to replace this K of S by, let's say, delta of S, reminding something uncertain there. Okay. So we know that basically so Y of S is going to be equal to G of S times U of S, whereas U of S is this R of s minus delta of s y of s, right. I'm showing these details, probably very familiar with some of these things. So after all said and done, basically you're going to get y of s as I plus g delta inverse g of s all of R of s, right. So I mean, this is in the multi-variable case. In the scalar case, this looks like something like y of s is equal to g by 1 plus g delta. And without going into too many details, basically the problem comes when 1 plus g delta becomes 0, right. Suppose if we assume that the system is stable when delta is 0, in that case basically y is simply g times r. So how much allowance can we have for delta before the system becomes stable? That's the question of robust stability, right. So robust stability is basically, the question is how big can delta be before the system becomes unstable. Okay. So we are talking about size of this particular delta essentially, and they are called stability margins, robust stability margins if we are directly dealing with, say, modeling the uncertainties. If you are dealing with, say, a control problem, then you'll have different kinds of margins there, gain margins and phase margins and whatnot, and all of them essentially talk about how much uncertainty can you allow, right. So in that sense, this robust stability is a unifying concept. So let's go back to this thing here, right, I plus g delta inverse g times r. So what will happen to this corresponding condition? Well, by extending wildly and intuitively speaking, whenever this determinant of this particular thing becomes 0, then we'll have trouble. So this condition kind of extends to determinant of I plus g delta is equal to 0. Okay. So we'll forget about the Nyquist plots at this particular point and just focus on this particular condition where my g is stable, right, and how much can I allow in terms of delta so that this determinant remains non-zero, and what's the first point it becomes 0, right. So that's the question that we have in terms of frequency domain condition for robust stability. But before that, there were many conditions in literature that kind of ensures stability of feedback systems, right. One of standard systems, standard results are, so if you have some system like this, okay, and somehow we can guarantee sigma max of g times sigma max of g hat is less than 1, then the feedback interconnection NFI, negative feedback interconnection, is stable. Okay. So what this is essentially saying that if you have two systems in feedback, if both are somehow less than 1, the sigma max is the maximum singular value. Hopefully you're familiar with that particular concept. It is actually a norm on matrices. So it captures a very well the size of any matrix and things like that. So so when we actually have this condition, then basically we can guarantee stability, and then this is called small gain theorem. Again, typically this is applied when G and K are K is a controller and things like that. If both of them have small gain, the system is stable, right? And there are nonlinear versions of this. Okay, the nonlinear versions go, and then we will go through some of these details. So some kind of nonlinearity, static nonlinearity, and you have this negative feedback interconnection. Something has to be true with this phi, and G has to satisfy this. Sigma max of G has to be less than 1, and also something has to be true about phi, then we can guarantee stability of the feedback interconnection. And this is kind of generalization of small gain theorem, right? So all such theorems existed, and the understanding of determinant of I plus G delta is 0 was understood for MIMO systems, but there was no simple way of computing, I mean, except this small gain theorem. Beyond that, there was nothing. What was the need? Well, let's take one straightforward example. Again, it's a theoretical example in the sense that, let's say I have this system A. Okay, I'm going to put a parenthesis there, right? And I have some kind of and I'm going to put a parenthesis here just to introduce more, right? There are two things going on here. So A, the parameter that we have in terms of understanding the stability and things like that, we analyze, we know that A, if it has eigenvalues in a certain way, then we have stability, right? But unfortunately, the knowledge of A could be incomplete, right? So that means we don't know exactly what is A, but there is some delta A that we don't know at all. But of course, we kind of know, perhaps is less than, I don't know, 0.1 or something like that. Okay. Similarly, here on the other hand, we assume that basically, let's say, some linear combination of X is kind of measured, but then this measurement is done through an instrument, and then every instrument has its own dynamics, right? So we actually, this is in fact equivalent to G of S. Y of S is actually equal to some kind of transfer function multiplied by C times X of S. Okay. So, but we really don't care about modeling this, or it's too complicated for us to worry about dynamics of that instrument and things like that. Perhaps we know that something is true about this instrument. Okay, some kind of size and things like that. Okay, perhaps that's also small. So in all these cases, we'll end up with a problem, and we'll show some examples at a later point when we actually present more theory. So we will end up with basically a problem where we have very well captured the what you call average behavior of the system through this G of S, and we'll assume somehow this is stable, right? If it is not, we will use a control to actually stabilize it. But we have to deal with this uncertainties that we haven't modeled. Okay. So what kind of uncertainties are there? I mean, it really depends on how we model it. Nice things to model them as actually keep them in a structure, and they end up having such a structure, some kind of bunch of parameters, scalars, matrices, and even transfer functions, right, coming from unmodeled dynamics, right? So you have this very beautiful structure for delta, okay, and then if we end up using say small gain theorem, which says that maximum singular value of both of these things have to be less than 1, we are in a way throwing out all the structure that is available in this particular delta, right? And more importantly, some of them are scalars, some of them are these things, and some of them are matrices, and they may have more structure to them. Delta could be real, complex, and different conditions will produce those kinds of things, right? I mean, when we get complex, typically when they are transfer functions, they could be scalar transfer functions, they could be matrix transfer functions. Sometimes these matrices are simply real numbers, perhaps. They have more structure to them. They are symmetric matrices and things like that. So all kinds of structures are possible. So, so the question of basically how do I ensure this particular condition, determinant of G delta being less than not equal to 0, And what is the smallest delta or the biggest delta where this condition is satisfied, or conversely smallest delta such that determinant of I plus G delta is 0, right? Smallest in the sense of some kind of size on the delta, right? And but respecting the structure is important, right? So in early 80s, basically the question of structured uncertainty. I mean, in the 70s, basically people understood this small Gaussian theorem and applications to unstructured uncertainty, where this big delta is some junk that is coming from unmodeled dynamics, everything, and then we treat it as just a big matrix that we don't know anything about, right? But the fact is, basically in typical applications, we have this beautiful structure, and we know the structure, and then perhaps even much more than that, things like symmetry and things like that. So how do we handle that kind of structure and get better results, right? What do we mean by better? Well, if we assume this delta is big matrix and we don't know anything about, basically the result that says is small Gaussian theorem, sigma max of G times sigma max of delta should be less than 1 to guarantee that determinant is non-zero, right? But if we have structure, perhaps we can actually allow much bigger than the sigma max plus sigma max times sigma delta being less than 1. Perhaps there is something else, right? So that was the question, and the answer was being searched by many people, but there were two players who finally succeeded in both eventually settled as faculty members in California, 2 universities, one at Caltech and the other one at the University of Southern California, Los Angeles, and both were excellent researchers. Both are excellent, excellent researchers, and then both published papers in 1982. But the work by John Doyle is much more accepted, and John Doyle, if anybody talks about it, basically they talk about this concept called structured singular value, right? And he gave a symbol for that, and then basically it's mu, and then ever since, basically whenever people talk about robust stability, immediately people talk about this quantity called mu, which operates on some matrix, and typically a complex matrix, and then it has become something called mu theory, okay, mu theorem or mu theory or whatever. And there's a whole lot of computation that can goes on in terms of linear matrix inequalities in the frequency domain. Okay, so what is essentially the idea is, I'm going to define that. So mu is defined as some quantity some minimum of sigma max of all deltas such that determinant of I plus G delta is equal to 0. Okay, and then put an inverse, and first look at itself is actually quite put off. It seems too complicated, but eventually the great marketing person that John Doyle is actually marketed this very well, more because not just because this definition is somehow made people like it, but much more provided properties of mu. In certain cases, this is identical to sigma max of G, and so on and so forth, and showed many interesting properties, right, for G. So we provided computation method to get close to mu. Okay, so without going too many details, that's the best I could do. So, if you actually look at it, basically what this is saying is we are interested in avoiding this particular condition, determinant of I plus d delta. So, find all such deltas, and then the sigma max is simply putting the size of it. Find the smallest of those deltas, and then take inverse. And this inverse has logic. If we didn't have that inverse, basically we would not end up with nice equations like this, and there are many results. Mu can be lower bounded by the spectral radius, or the absolute value of the maximum eigenvalue and things like that. So there are many nice properties that come from mu simply because of the inverse. And then Michael Safano, who also produced this particular theorem, he didn't have this inverse, and perhaps that's one of the reasons that his concept, though identical, did not become popular. But eventually all of them, when it comes to practical stuff in terms of computing, they are identical to one another. And I could go on and on, talk about mu theory for the longest time, but that's probably another course. I will straight away jump into basically how we can deal with them in state space theory, and then show some connections to mu as and when it is appropriate, right? And when we actually move to state space theory, it becomes quite obvious in terms of how to deal with various types of uncertainties. We'll start slow. We'll start with linear systems, then add nonlinearities, nonlinear systems, and things like that in the next couple of lectures. And beyond that, we will present a very generic theory that subsumes all of these things, and then if we understand that particular theory called dissipative theory, all of these things become a corollary, right? But then it's equally important to understand the general theory and their applications to various cases, and then we keep going back and forth and connecting some of the more general concepts. When we present it, we will show how they apply to robust stability and things like that. Okay. So before I close this particular lecture, brief introductory lecture on robust stability, I want us to understand, suppose if we have a system So before we close this introductory lecture, I want to briefly discuss about the alternative approach to robust stability. Well, I mean, in my opinion, both are equally important, and basically a combination of these two will actually fetch a very practical approach to control systems. Suppose we have x dot equals ax t plus some kind of b times u, or something where b times u is the control part. Thing is, we want to stabilize this particular system. The problem is a is completely unknown. Okay. What more, we don't know any bounds. If we had bounds, then basically we go to the robust stability kind of approach, which is ideal. Basically, we have seen, we can get margins for a set of uncertainties and things like that. But if it is unknown, but we have no clue in terms of its bounds, so what do? There was a concept, we will talk much more at a later point, but there is a concept called adaptive control, okay, where at least theoretically speaking, basically we are going to somehow figure out a control that is magically going to adapt to this unknown value of a, right. So in a sense, basically somehow if we can estimate the value of a and use that estimate in your control, then perhaps we will get far better performance, right. So the thing is here, it's it's some unknown number, whereas in typical robust control we assume that it's unknown, but it's between some numbers. So we want to do a job where the system is stable for all kinds of uncertainties. Here, no, I know one single uncertainty, it's just that I don't know the value. So can I actually somehow figure out a way of estimating while trying to control it, right? So that's called adaptive control, and we will look at it, and both have its own disadvantages and advantages. And like I said, when one cannot ignore the robust control for adaptive control and vice versa. It's the understanding of both of them, and then as and when what is required one has to use. So this also depends on your Lyapunov function theory. So it's not like we are moving away from anything that we have been discussing. So that's going to be one of the lectures at a later point, right? We'll start with linear systems and robust stability, and then include nonlinearities, and then go to results on something called dissipativity, and then look at applications like adaptive control, and then finally optimal control. Okay, with that, I thank you.